Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and tonight I'm going to introduce to you a subject that I took and I loved it very much called material science. And what you see in material science are different materials that we use every day. And are also bonds that you have to know, like covalent bonds, non covalent bonds. You have phase systems. You have different testing, mechanical, electrical. And this course is a good course if you are into becoming a material science engineer. Now, not too many schools have this program, but the schools with a big name, like one about 60 miles northwest of me, which is one of my alma maters, Purdue University, they have material science. And when you actually understand material science, you're going to see how materials built. You're going to see the cooling process. And within material science, you're actually going to get an idea of heat transfer. You're going to get thermodynamics. Now, this course is particularly important if you are going to sit down and take the fundamentals of engineering examination. Now, believe it or not, materials don't just include polymers, metals, plastics. Now, everybody is thinking, okay, this is for mechanical engineers. No, concrete is involved in that as well. So if you are a civil engineer, mechanical engineer, you're talking about circuits, electrical engineers, this is the course for you as well. So what I'm going to do, I'm going to share my screen and I am going to talk to you about materials science and engineering. And right here on the first slide, this is where you have shapes, covalent, bonds, non-covalent bonds, just as I mentioned before. So to start everything off, get everybody on board with the introduction. Well, what is material science? Well, it's a branch of science that focuses on materials. It's an interdisciplinary field that's composed of physics and chemistry. And it has a relationship of material properties to its composition and structure. So, what is a materials scientist? It's a person who uses his or her combined knowledge of physics, chemistry, and metallurgy to exploit property, structure, combinations for practical use. Think about that. A material scientist is a person who uses his or her combined knowledge of physics, chemistry, metallurgy to exploit property, structure, combinations for practical use. Now, what are materials? And what do we mean when we say materials? Well, we have a few of them. We have metals. Now, metals are used in mechanical engineering and, of course, civil engineering. And under metals, there's aluminum, copper, steel or iron alloy, nickel, and titanium. We get into ceramics, clay, silica glass, alumina, and quartz. And we get into polymers. And you're going to hear this term if you work in construction. Polyvinyl chloride. Now, when we talk about polyvinyl chloride, we mean PVC. Now, what material uses polyvinyl chloride pipe? It's known as PVC pipe. Then we have Teflon, various plastics. What about adhesives? Glue, that's an adhesive. And for individuals who are out there in combat, Kevlar helmets. And then getting back over to my field of civil engineering, composites. So that's the area where you have wood, carbon fiber risers, and concrete. So if you look at everything, when it comes to materials, it's in a number of branches of engineering, but you also have semiconductors, computer chips, and that equals ceramics, composites, nanomaterials, and that also equals ceramics, metals, polymers, and composites. So the length scales of material science. Well, something that you need to know, atomic is less than 10 to the negative 10 meters. Nano, 10 to the negative 9 meters. Micro, 10 to the negative 6 meters. And macro, 10 to the negative 3 meters. Now, when I'm giving you the scientific notation, when I say anything to the negative power, that means 1 over that number. Like 10 to the negative 3 is 1 over 1,000. That means 1,000, it's really 1 over 1,000, or we can say 10 to the negative 3. And as you look at what's in materials, you have automatic handwriting, you got a big motor, nanoshells, a quantum coral, nanostructure, medication delivery system, a nerve chip. You have a man standing at 6 feet tall. Then you have your DNA. This is a helix. And you have your blood cell. And this is what materials are tied to. Now, looking along this scale, so you know, this is where we start to see the 10 to the numbers here. We have picometer, what we call it picometers. That's trillions. Your nanometers, billions. Your micrometers, millions. Your millimeters, thousands. Your centimeters, hundreds. And your decimeters to your tens. So you have, again, picometers, trillions, nanometers, billions, micrometers, millions, millimeters, thousands, centimeters, 100s, and decimeters, tens. Now, these numbers are very, very small. Very, very small. Now, when we talk about our atomic structure, we're talking about 10 to the minus 10. It pertains to atom electron structure and atomic arrangement. Atomic length scale, which includes electron structure and atomic bonding. So this is what I mentioned earlier. You have your ionic, your covalent, your metallic, and your London dispersal forces, which is van der Waals. Then you have your atomic ordering, long-range metals, short range glass. We have 7 lattices, cubic, hexagonal, among most prevalent for engineering, metals, and ceramics. Then you have different pack structures, and they include, and the inclusion gives you a total of 14 different crystalline arrangements, your bravas and your lattices, your primitive, your body center, and face center. And this is where you start getting in your chemistry right here. This is right here, 1e. What is 1e? It means it's 1 electron. 2e, 2 electrons. We get into 10 to the negative ninth length scale that pertains to clusters of atoms that make up small particles or material features. Show interesting properties because of the increase in surface area to volume ratio. So what happens is you have more atoms on surface compared to bulk atoms. And then we start to get into things you see with your eyes. We deal with optical, magnetic, mechanical, and electrical properties change. And this is under the nanostructure. Then we have your microstructure, 10 to the negative 6. Larger features composed of either nanostructured materials or periodic arrangements of atoms known as crystals. Features are visible with high magnification in light microscope. Grains, inclusions, other microfeatures that make up the materials. These features are traditionally altered to improve performance. Find that in cars. You'll see that you'll have it in this car. Then we have our macro structure, 10 to the negative third, pertains to collective features on the microstructure level. Grain flow, cracks, porosity are all examples of microstructure features. Now, where's another place that you see the word porosity? Well, you see it in fluids and you also see it in soils. Then we have all that. Let's get into the classes of materials. We have your metals, your polymers, your ceramics, and your composites. And again, these materials are used for everyday items that we use, like milk cartons, scales, cars. And we have our material applications, electrical wire, aluminum, copper, silver, heat transfer fins, aluminum, silver, plumbing, copper, construction beams, used for bridges, skyscrapers, rebar, etc. Steel, FEC alloys, cars, steel, FEC alloys, consumer goods, soup cans, appliances, stainless steel sheet metal, utensils, tools, and of course, many more. And for the metals, metals consist of alkaline earth, metalloids, and transition metals. So basically, metal alloys are mixtures of 2 or more metal and non-metal elements. For example, aluminum and copper. Copper and nickel, alloy steel. We have our bonding, metallic bonding. No particular sharing or donating occurs. Electron cloud is formed. That is free electrons. Strong bonds with no hybridization or directionality. Then you have your properties. Electrically conductive, free electrons, thermally conductive, high strength, just large capacity to carry load over X section area. You deal with stress. Ductile, endures large amounts of deformation before breaking. Then we have magnetic, ferromagnetism, and paramagnetic. Then we deal with the medium melting point. Polymers consist of various hydrocarbon organic elements with selective additives to elucidate specific properties. Polymers are typically disordered, amorphous stands of hydrocarbon molecules, bonding, covalent, London dispersion forces, and we have our properties. Ductile can be stretched up to 1000% of original length. Lightweight features low densities. Then we have medium strength, depending on additives. Chemical stability, inert to corrosive environments, and a low melting point. Polymer applications, car tires, vulcanized polymer, added sulfur, Ziploc bags, food storage containers, plumbing. When I told you about PVC, well, this is where the pipe comes into play. Polyvinyl chloride, PVC, Kevlar, aerospace and energy applications, Teflon, consumer goods, calculator casings, and here's an example of a calculator casing. TV consoles, shoe soles, cell phone casings, Elmer's glue, which is an adhesive, contact lenses, and many more. Ceramics consist of they consist of metal and non-metal elements. Again, ceramics consist of metal and non-metal elements, typically a mixture of elements in the form of a chemical compound. For example, aluminum trioxide. Now, what is aluminum trioxide? It's glass. Then there are three types of ceramics. We have our composites, monolithic, and amorphous ceramics, bonding, covalent, ionic, typically covalent. In some cases, highly direction covalent bonding, ionic in case of silicon oxide, glasses and slags. You even learn about the periodic table here. Then we have our properties: wear resistant, hard, chemical stability, corrosion resistance, high temperature strength, strength retention at very high temperatures, high melting points, dielectrics, which are good insulators, adhesives, good optical properties. The applications, or we call them ceramic applications: window glass, Al2O3, SiO2, MgO, CaO, calcium oxide, magnesium. No, magnesium, I believe magnesium might be Mg or Mn. I know aluminum trioxide. So knowing those elements, study chemistry. Well, also in ceramics, we have aerospace, engineering, and automotive industry. Aerospace, energy, and automotive. Heat shield tiles, engine components, reactive vessel and furnace linings. And then we have consumer products under ceramics. How many of you all have done pottery? Well, you know, pottery is a ceramic. What about dishes? Fine china, plates, bowls. What about glassware, cups, mugs, etc.? And these eyeglass lenses. Composites. Well, it's a mixture of two different materials to create a new material with combined properties. Types of composites: particularly reinforced, discontinuous type with low aspect ratio, whisker rod reinforced, discontinuous type with high aspect ratio, fiber reinforced, continuous type with high aspect ratio, naturally. Laminated composites, layered structures, surfboards, skateboards. Now the bonding depends on the type of composite: strong covalent, medium solid, solution, weak, tertiary phase layer. Then we have our properties. Just depends on the composite. High melting points with improved high temperature strength, ceramic. High strength and ductile with improved wear resistance, metal ceramic. And we have high strength and ductile, polymer. Now the composites, one of my favorites because I work in construction. Wood, naturally occurring biological material that consists of very strong fibers embedded in a soft matrix. Plywood, laminated wood for buildings. Concrete, you use concrete for basements, bridges, and sidewalks. Fiberglass, boats. Carbon fiber risers, you can use that for bicycle frames. Advanced applications, ceramics and composites, aerospace and defense applications. So basically, these are structural materials used for missiles, aircraft, space vehicles. What type of materials may be used? Well, you have ultra high temperature ceramic composites, metal, non-metal, covalent bonded compounds, high melting point materials, strong materials at temperature, excellent oxidation resistance. Why these materials? Surface temperatures are in excess of 2,000 degrees Celsius, 1/3 surface temperature of our sun. Also, materials have high melting points, which are greater than 3,000 degrees Celsius. Excellent strength retention at surface temperatures, relative chemical stability at surface temperatures, and also lightweight. Advanced applications for ceramics and composites, structural materials in use for hypersonic aircraft, next generation reentry vehicles. What is the space shuttle shaped the way it is? Well, why is it shaped the way it is? And here's what you see: to reduce the amount of heat generated upon reentry. And when we talk about reentry, that is from the ozone, the atmosphere. Also, UHTC materials can change the shape of the next generation space planes because of their unique combinations of properties. Advanced application polymers, self-decontaminating polymers. Well, they're in medical, military, security, and environmental applications. Current applications. So basically, you look for attachment to textiles for self-toxin cleaning fabrics. That is chemical scavenging and cleaning clothing. Then we have our sulfonated polyether polytherketone, or we call it speak. That's polytherketone, and of course our polyvinyl alcohol PVA aqueous solutions. Not bad on the pronunciation. If you are in the health field, you can definitely pronounce those words, but you know you're dealing with chemistry. And then we get into our excite solutions with light to form strong reducing polyzinphenol ketone BBK radicals, which helps break down organic toxic materials. Advanced application metals, hydrogen absorbing metal alloys for energy transportation or batteries. So you have your electrolyzed hydrogen from water. Fuel cell technology can be stored in tanks fabricated with hydrogen absorbing metal alloys. Then you have your nickel metal hydride. Batteries use the same principle, but to improve battery self storage. Volume density is significantly higher for gaseous hydrogen and more hydrogen per tank. Then we have our typical alloys. They consist of all of these chemical compounds that you see. MnTIV, Mg, Ni, which Ni I know is nickel, Cr. Mn I know is probably, I believe Mg is magnesium. La, Ni, I know, like I said, Ni is nickel. Then you have BCC materials. They show higher storage and desorption properties. Some materials can absorb a gas densities equivalent to hydrogen densities. Other well-known materials, semiconductors, ceramics, computer chips, memory storage devices, solar cells, image screens, non-materials, ceramics, metals, polymers, gold nanoshells, quantum dots, ferrofluids, medical devices. Now, how do we test the materials? We use mechanical, chemical, and optical methods. Mechanical testing gives strength, ductility, and toughness material information. So this is where, because I work in construction, I use some of these tests: fracture testing, compressive test, bend test, tensile test. Now, chemical testing tells us about the composition and chemical stability, X-ray diffraction and fluorescence, composition testing, corrosion testing. Then you have optical testing is more of a way to view atomic, nano, and microstructures. And it also gives us insight to structure property relationships like light optical microscope or microstructure, scanning electron microscope, microstructure and nanostructure, transmission electron microscope, nanostructure and atomic structure, scanning tunneling electron microscope, atomic structures. Now, mechanical testing. Now, this is one that I'm familiar with. This is what we call our basic stress strain curve. It's created from experiments using the test frame. Again, you have your schematic stress strain curve created from experience using universal test frame. Now, you're going to see this in another course called mechanics of materials. So basically, you have your curve. Now, this is your offset. And this is your force over your area. And this is your, I think it's your elasticity. That's your length. And here you have a rod that's being tested. And what you're doing, you're going to basically pull that rod until it breaks. So what you're going to have here, you're going to go all the way up here. And then at the last moment, if you have a point number 5, that's when it breaks. That's why that graph looks like that. Mechanical testing. And here are your machines. This is one that I'm familiar with. They're breaking wood. Here's another one. It's like they're breaking glass. They're breaking bone here. That's why we use all kinds of tests. We want to make sure that we're working everything for strength, durability. Mechanical testing. What is stress and strain? It is like forces and length change. It's known as displacement. That's when your forces and your lengths change. Stress is defined as the force per unit cross-section area. S equals force divided by area. Strain is defined as the ratio of length change to original length. So I said your big E is your elastic, and your little epsilon, that's your strength. And here is the formula. Now, why use these terms? Stress scenario. So basically, if I apply a force on an eraser of a pencil and apply the same force on a tabletop, how does each material behave? Can you distinguish which material is stronger? Force as a strength description is inadequate because different sized objects accommodate the force differently. So just because both objects can handle the same force does not mean they are the same strength. Strain scenario. If I pull on a 1-inch long piece of taffy and apply the same pulling force on a piece of 2-inch long putty, and both have equal diameters, with the taffy and putty stretching the same distance, what does it say about the two materials? They both stretch the same distance. However, displacement only cannot distinguish materials that can accommodate large deformations or changes in shape. Thus, the taffy can accommodate larger shape change because the ratio of length change to original length is simply larger than the putty. Chemical methods, X-ray diffraction, mass spectro, spectro, uh, spectroscopy, that's mass spectroscopy, gas chrom, chrom, chromatography, that's chromatography. So we have X-ray diffraction, mass spectroscopy, gas chromatography, and then we have our X-ray fluorescence. X-ray diffraction, mass spectroscopy, gas chromatography, and then we have our X-ray fluorescence. Very good pronunciation. And then last but not least, here are our viewing methods. So when you deal with chemistry, you're going to be looking at materials through a microscope. So you scan the electron microscope. You have the atomic force microscope, optical light microscope, and your transmission microscope. But the materials that you've seen are used in our everyday products. And if you're in engineering, those materials are used over all branches of engineering. Now, you must understand that engineering is made up, before the math comes into play, it's made up of actually three sciences, three branches of science. And what are they? Physics, chemistry, and biology. And then when you put the math is just to give you the theory. But once you get into theory, then you get into the application. Now, what's involved with the application? That's the testing. And again, materials have to be tested to make sure that they're workable, they're durable. We also have to make sure that we understand the cooling and the heating process of materials. That's why material science is very important. And we're talking about all materials. You know, even when you are baking bread, what material are you using? You're using flour, using water, you're using yeast. It's a material. And when you start getting into the thermodynamics part, then you start getting into the convection and the conduction part as well. And then when we start to deal with temperatures, start to get into Kelvin and Rankine. But overall, I just wanted to bring you some insight on material science and how materials affect our everyday lives. And many of us who don't understand materials, we take it for granted. So I wanted to give you a breakdown of what's involved when it comes to these materials. And it's very important that you understand how these materials work, because these materials, they're not going away. You have your plastics. That's why we have recycling. Also, we have materials, they're used mechanically, electrically, and physically. That's the main points that you need to know how these materials are used. Again, use materials for cars, buildings, medicine, for humans. And when it comes to engineering, all branches of engineering use chemicals. And that concludes this topic on an introduction to material science. If you like what I just presented, please comment, share, and subscribe. And if you are looking for some social and political issues, check out my main channel, the 411 Telephone Radio Show. Now, here's where you can find me. The 411 Talk Zone Radio Show channel, you can find me right here on YouTube. You can find me on X, formerly Twitter, Truth Social, and Rumble. For the QCIS channel, you can find me right here, YouTube, X, formerly Twitter, and LinkedIn. Once again, thank you for viewing this content on Introduction to Material Science, the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.